Okay, so this first one here, where do we start at? -2. So there's our first point. From there we go up 3 over 4. So you got to remember when you're plotting a point, it's horizontal first and then vertical. But when we're doing slope, it's vertical first, then horizontal. How many people got that for that first equation? Beautiful. Second equation, where do we start? +3. So there's our first point. From there we go
Down 2.
Perfect. Down 2 over 3. Third equation requires a little bit of work. Everything we've done so far has been x equals CS. Exactly. We divide by 3. Oops, that should be a 3 there, not a 1. So the 3 divides out. When we multiply or divide an equation, we have to multiply or divide every piece of it. So we divided out the 3 from that piece, equals 6x divided by 3 is 2x. -3 divided by 3, -1. So where's that one start? -1, and from there we go up 2 over 1. Yeah. A lot of times it's easier, so we make that a fraction by doing 2 over 1. And a lot of times something like that, it's easier if I go up 2 over 1 again and maybe even a third time just to make sure I'm going straight up the graph. Number 4 here. Yes, we have to subtract 3. We've got y plus 3. So we subtract 3 from both sides. When we subtract or add in an equation, we only have to do it to one piece on each side. So we have y equals, the x over 2 is not changed. 2 minus 3 is a -1. So this is going to start at -1. What's it going to do from there? Up 1 over 2. Good. You got to realize that x over 2 is really a 1/2 x. So you got 1/2 slope. And finally, number 5 here, what do we have to start off doing? We subtract the 3x. So 2y equals 4 minus 3x. And yes, we do divide by 2. So y equals 4 divided by 2 is 2, and -3x divided by 2. Yeah, -3 over 2, or -3 halves, or 3 seconds x. So we start at 2, and from there we go down 3 over 2. Looks like we're doing very well with the graphing there. So I want to try this. Y equals 2/3 x minus 1, and y equals -1/2 x plus, yeah, it's going to be 6, plus 6. I'm going to graph both of those quick. So, top equation, where do we start? -1, from there we go up 2 over 3. I'll do it again, up 2 over 3. Pretend that's straight, but I made my graph okay. What's that? I just did it twice to make sure I kept going straight. The next one, where do we start? 6, so up here, and from there we go down 1, over 2. I'm going to do it again, down 1, over 2, maybe one more time. So here's the question. What does that blue line represent? It represents all the solutions to this equation. Any point on that line, like right here, I can take its x coordinate and its y coordinate. That is x equals 1.5, y equals 0. If I put that in here, it's going to make it true. 2/3 times 1.5 is 1. 1 minus 1 is 0. That's true. 3, 1. If I put that in there, it's going to be true. 2/3 times 3 is 2, minus 1 is 1. It makes that true. Any point on that blue line, if I take its x and y coordinate, it will make that equation true. That is a picture, a graphical representation of all the solutions to that equation. So then, of course, the red line is all the solutions for this equation. Every point on that line, if I take its x and y coordinate, it will it'll make that equation true. What we're going to start looking at today is something we call systems of equations. In a system of equations, what we are looking for is values that make both equations true at the same time. Looking at this graph, where on that graph are both equations true? Yeah, where the two lines cross, right there. And that's why, I was very, very careful to plot this one out. That point is at 6, 3. 6, 3 is the one point, the one value for x and y that'll make both equations true. If I put 6 in here, 2/3 times 6 is 4, minus 1 is 3. If I put 6 in here, negative 1/2 times 6 is negative 3, plus 6 is 3. So it makes both equations true. And the simplest way to solve a system of equations, at least when it's two variables, is to just graph and look for the intersection. So I might have something like this. Try that one. Try to graph those two and see if you can figure out the solution to that system just by graphing. Okay, so for the first one here, we have to divide by 2. So we get y equals x over 2 minus 1. So we're going to start at negative 1, up 1 over 2, right? For the second one, what do we have to do to that one? Subtract 3. So y equals 3/2 x plus 1. So we're going to start out up here, and we're going to go up 3 over 2. What'd you get for the solution? Negative 2, negative 2. Very good. As you can see with graphing, you have to be very, very careful to get the solution. And also, if my solution were something like Yeah, you're not going to find that on a graph. Not unless you do some sort of electronic graphing. And we're not going to get into that. I figure you guys can learn different technologies later if you want to. So most of what we're going to do is going to be pretty straightforward, integer, no fractions, no decimals for solutions. Starting tomorrow, we'll start looking at algebraic methods of solving these equations where you can calculate that exact answer.
By manipulating those two equations with each other.
Yes. So for now, I'm going to have you guys work on page 409. It's exercise 17-1. It's problems 1 through 17. I don't necessarily expect you to even do all the odds. I know that's 9 of them, and it's a lot of drawing out graphs. Do enough of them. Make sure you skip some of the harder ones where you do have to rearrange the equations to graph them. And one thing I always recommend is test the points back in. I didn't do it on this last example, but up here, I took that point, I found 6,3, and I put it back into each equation and made sure it made both equations true. It's always a good idea when you're graphing just to make sure you graphed it straight. So we'll have you work on that, and we'll give you the last 15 minutes to do those.
So you would just equal